Welcome to the Greek Ship Corrosion channel. My name is Maryam Ehteshamzadeh. I'm a researcher in the field of corrosion and protection of materials. Chapter 2, Section 7, Thermodynamics of Electrochemical Reactions, Nernst Equation. Our main reference is Fundamentals of Electrochemical Corrosion, ASM International. First of all, calculation of the change in the GFE. Consider the generalized electrochemical reaction. X moles of M plus M moles of XX plus double arrow X moles of MM plus M moles of X. The double arrow implies that the reaction is going in both directions, either left to right or right to left. One of the most significant equations derived from chemical thermodynamics permits calculation of the change in the Gibbs free energy for this reaction at constant total pressure and temperature as a function of standard Gibbs free energy of formation of the reactant and product species in their standard states and the concentrations of those species with concentrations that can be varied. The equation is delta G reaction equals delta G not reaction plus RT ln the activity of X to the power of M times the activity of Mn plus to the power of X over the activity of M to the power of X times the activity of XX plus to the power of M. In this ratio, the A's are the activities of the species indicated by the subscripts. Each activity is raised to a power equal to the stoichiometric coefficient of the species as it appears in the reaction. Delta G naught of the reaction is the change in the GFE for the reaction as written for reactants and products in their standard states. It is calculated from the following equation. Delta G naught reaction equals the summation of standard Gibbs free energy of formation of products minus the summation of standard Gibbs free energy of formation of the reactants. Calculation of standard change of GFE for chemical reactions from Gibbs free energy of formation is available on this channel, slide number 187, in the video titled Chapter 2, Section 2. Standard state. The standard state for reactants and products in this reaction is pure solid for solid species, 1 atmosphere pressure for gas species, and unit activity approximately unit molality for ionic species. Standard state denotes the most stable state of the element or compound at a given temperature, mostly 298 Kelvin. If you have a reaction at standard state, you know the reactants will appear in their most stable forms. For water, it is H2O in the liquid state, and for oxygen, it is O2 in the gaseous state. Activity and molality. The activity is frequently called the effective concentration of species because it naturally arises as a function of the concentration that is necessary to satisfy the changes in the GFE or other thermodynamics functions. In electrochemical systems, the activity is usually related to the molality of the species moles per 1000 grams of solvent by the following equation. A equals gamma times M, where gamma is the activity coefficient and M is the molality. Measurement or calculation of accurate activities in concentrated electrolytes and in electrolytes of complex mixtures is generally not possible. Also, a tenfold change in the concentration results in a change of less than 100 millivolts in the electrode potential, which is frequently small compared to the potentials involved in cell reactions, that is, E cell values. And finally, metal ion concentrations in many corrosive environments are usually small, less than 10 to the negative power of 4, in which case the activity coefficient is essentially unity and therefore the activity is almost equal to the molality. Non-standard change of GFE for chemical reactions. If under the actual conditions of the reaction one or more species or solids or a gas exists at 1 atmosphere pressure, then unit activity for each of these species is substituted in the top equation, which effectively removes these activities from the logarithm term. Also, the activity of water can usually be set equal to unity because its concentration changes insignificantly in most reactions in aqueous solution. Thus, taking M and X as solids, the top equation reduces to delta G reaction equals delta G naught reaction plus RT ln the activity of Mn plus to the power of X over the activity of XX plus to the power of M, or non-standard Gibbs free energy of the reaction equals standard Gibbs free energy of the reaction plus this sentence. In this equation, this ratio is called the reaction quotient, Q, that is a dimensionless quantity that provides a measurement of the relative amounts of products and reactants present in a reaction mixture for a reaction with well-defined overall stoichiometry at a particular point in time. So, non-standard change of Gibbs free energy for the reaction equals standard change of Gibbs free energy for the reaction plus RT ln Q. This sentence reflects the deviation from the standard state. The Nernst equation. This generalized electrochemical reaction is the sum of the following half-cell reactions: X moles of M double arrow X moles of Mn plus X times M electrons, and M moles of XX plus X times M electrons double arrow M moles of X. Double arrow indicates that the reaction is reversible. We know that non-standard Gibbs free energy change of the reaction equals standard Gibbs free energy change of the reaction plus RT ln the activity of Mn plus to the power of X over the activity of XX plus to the power of M. Also, from the previous videos, non-standard Gibbs free energy change of the reaction equals negative X times M times F times E cell. F is the Faraday's constant, and standard Gibbs free energy change of the reaction equals negative X times M times F times E naught cell, or standard cell potential. Dividing both sides of the GFE change equation by negative X M F yields E cell equals E naught cell minus RT over X times M times F ln the activity of Mn plus to the power of X over the activity of XX plus to the power of M. From the convention relating the cell reaction to the cell representation, the video titled Chapter 2 Section 4 on this channel, the cell potentials are written as E cell equals E prime RHE minus E prime LHE equals E prime XX plus minus E prime MMM plus. And for standard state, E naught cell equals E naught RHE minus E naught LHE. That is, standard cell potential equals standard right hand electrode potential minus standard left hand electrode potential equals the standard potential of the half cell XX plus minus the standard potential of the half cell MMM plus. Substitution of the recent equations into the cell potential yields E prime x x x plus equals E naught x x x plus RT over x f ln the activity of x x plus, and E prime m m m plus equals E naught m m m plus RT over m f ln the activity of m m plus. E cell equals E naught cell minus RT over x times m times f ln the activity of mm plus to the power of x over the activity of x x plus to the power of m, and E cell equals E prime RHE or right hand electrode minus E prime left hand electrode equals E prime x x x plus minus E prime m plus. Therefore, E prime x x x plus minus E prime m plus equals E naught x x x plus RT over x times f ln the activity of x x plus minus E naught m plus RT over m times f ln the activity of m plus. Therefore, E prime x y z equals E naught x y z plus RT over n f ln or natural logarithm of the pi of the activities of the species in the oxidized side to the power of nu I over the pi of the activities of the species in the reduced side to the power of nu I. This is Nernst equation in which x, y, and z are symbolic representative of the important species involved in the reaction. The mathematical sentence in the numerator is the product of the activities of the species in the oxidized side, the side showing electrons produced, each raised to its stoichiometric coefficient nu I. The mathematical sentence in the denominator of the fraction has similar meaning for the reduced side of the reaction, and n is the number of moles of electron produced or consumed per unit of the half reaction. Thank you for your time and your attention. Challenge number 16. If you like to challenge yourself, please answer this question in the comments below. Who was Walther Hermann Nernst?